Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics on mathematics and pretty much any college mathematics course, please consider subscribing to our channel and then checking out our playlists, watching videos, liking, sharing, commenting on those videos. All those things help our channel out, and we greatly appreciate it. Let's get into the current video. I want to take a look at the interior of a set in a topological space and take a look at a couple of properties of the interior and prove those as well. So let's take a look at the definition of the interior of a set. So definition for a set A contained in X in a topological space X tau the interior of A, which is denoted int of A. You'll see some different notations depending on what textbook you're using, but in this video I'm going to use the notation int of A, again to denote the interior of the set A, is given by the following. Okay. Before I write the definition of what it's equal to, let me just kind of give you the general idea. The interior of a set is the largest open set contained within A. Okay. Therefore, this is equal to the union where of the set, let's say U, where U is a subset of A and U is open. In other words, it's the union of every single open set contained in A, and of course we know that even if this is an uncountable union or even countable, it still is going to be open because in a topology the arbitrary union of open sets is open. So the interior of A is the union of open sets contained within A. Okay. Let's take a look at a specific, here, let's make a quick note on that. For every subset of X, the interior of A is an open set. Again, it's a union of open sets, therefore must be open, and in particular for any set A, the interior is an open set. Let's take a look at a specific example, or a couple examples here. So let's say my set A is given by, or no, let's start with a set X. Let's start with the large space. Let's say that a set X is given by the following list of numbers 1, 2, 3, 4, 5, and 6. And let's give a topology on that. Let's say this topology tau, again, empty set containing X. Let's say I've got the singleton 1. Let's say I've got the set 2, 3. Let's kind of build this as we go. Well, if it has the singleton 1 and it has 2, 3, it has to have both the union and intersection. Intersection would be empty, and the union would be 1, 2, 3. Let's say we've also got the set 2, 4, 6. So then if I've got 2, 4, 6, I also have to have the union and the intersection with everything else. Intersection empty says empty. Intersection with X is 2, 4, 6. Intersection with 1 is empty. Intersection with 2, 4, 6 would be the singleton 2. Intersection with 1, 2, 3 would be the singleton 2, and then intersection with 2 would be the singleton 2. And then unions, 2, 4, 6 with the empty set would be 2, 4, 6. 2, 4, 6 with X would be X. 2, 4, 6 with 1 would be 1, 2, 4, 6. 2, 4, 6 with 2, 3 would be 2, 3, 4, 6. And then 2, 4, 6 with 2 would be 2, 4, 6. 2, 4, 6 with 1, 2, 4, 6 would be 1, 2, 4, 6. And then, let's see, so then I've got 2, 3, 4, 6 with the singleton 1 would be 1, 2, 3, 4, and 6. And I think that should be just about everything. Every union intersection of those should be contained in there. And therefore that is going to be my topology. Now let's say I've got the set A, which is a subset of X, and A is going to consist of, let's say, 2, 4, let's say 2, 3, no, let's say 2, 4, let me see, I want to try to pick one. Again, I'm just kind of making this up as I go. I don't want it to be open itself. So let's say if this is 1, 2, 3, 4, 6. Okay, so there's my set A, which is, of course, is a subset of X. Now let's look at the interior of A. So the interior of A. Again, it is, I can look at it according to the definition, or I can give you the interpretation that I gave originally, which is the largest open set contained in A. So let's look at it both ways. Well, the largest open set that's contained in A, 1, 2, 3, 4, 6, well, 1, 2, 3, 4, 6 is actually, oh, dang it, that is actually a element of the topology. So therefore the interior of A is itself, which is 1, 2, 3, 1, 2, 3, 4, and 6. Let's do another example within that. Let's say the set B is, let's say it is 2, 3, 4, 5, 6. That's not open because none of my open sets have the element B, for example. But let's say if B is 2, 3, 4, 5, 6, what is the largest open set contained within that? Well, I know 2, 3, 4, 6 is open, so therefore, and that doesn't have 5, so therefore the interior of B is 2, 3, 4, and 6. Now, of course, I could have also taken every possible open set that's contained in B. For example, let's see, I've got 2, 3, 4, 5, 6. Therefore, the open sets contained within B would be the empty set, 2, 3, 2, 4, 6, 2, 2, 3, 4, 6. Take the union of those, I'm going to get 2, 3, 4, 6. So again, depending on your situation, I might be able to just look through this really short finite list and find the largest open set contained in it, or I could just take every possible open set and take their union. So again, it just depends on the situation that you have. But again, in this case here, we see that the interior of A was actually A itself, and of course here, when I had B, the interior of B was a strictly smaller set. Okay. So let's take a look at another example. Okay, let's look at the next two examples. I'm going to take the topological space consisting of the real line and the usual topology. Again, that's just a topology that you're familiar with from, say, your calculus class, so like open intervals are open, so on and so forth. So let's say part A, I've got the interval from 0 to 4, where 0 is included but 4 is not. Let's find the interior of that. And then part B, let's find the interior of the set of rational numbers. Of course, set of rational numbers is a subset of the real numbers. For example, part A, the interior of 0 to 4. Well, let's think about that. So 0 to 4, of course, is not an open set because it contains one of its boundary points, which is 0. But I do know that the set 0 to 4 is open, and 0 to 4, of course, is a subset of the interval from 0 to 4, where, of course, 0 is not included in the former set, but 0 is included in the latter set. Now, is this the largest one? Well, if there was anything in between here, the only set that's in between the open interval 0 to 4 to this half-open interval 0 to 4 would be the half-open interval 0 to 4, which, of course, is not open. Therefore, we know that the interior of the half-open interval 0 to 4 is the open interval from 0 to 4. Okay. Part B. The interior of the rationals. Well, let's see what we can say about an open subset of the rationals. Again, the interior of the rationals is the union. Let's interpret it this way. Rather than thinking about the largest open set contained in it, let's think of it in terms of it's the union of all the open sets contained in it. So what I want to do is let's say let U be a subset of the rationals where U is open. Use an open subset of the rationals. So the question is the set U empty or non-empty? Okay. Clearly the empty set is open and is a subset of the rationals. So let's say, suppose that this set U that I'm constructing is non-empty. Okay, so let's say U is non-empty. Well, then there exists an X in U. If it's not empty, then it must contain something. And if it's open, okay, then that implies if it's open, then there must be a neighborhood of X that's contained in U. So there must be a delta positive for which X minus delta, X plus delta is contained in the set U. In other words, there's a delta positive such that the delta neighborhood of X, in fact we'll say the deleted delta neighborhood of X, is contained in U. Actually, no, we don't need it to be deleted. No. Okay, so let's say the delta neighborhood of X is contained in U. Well, the irrationals. So, however, the irrationals are dense in the real line. So there exists an alpha which is contained in this delta neighborhood of X, where alpha is an irrational number, but then that delta neighborhood is not a subset of U because it contains an irrational number. Therefore, U must be an empty set. And what this tells me is that no matter what subset of the rationals I pick, if it is open, it must be the empty set. Well, if I have every possible subset of the rationals that is open is empty, and the interior of the rationals is the union of all of those, well, clearly that then states that the interior of the rational numbers is empty. Okay. All right, let me wrap up this video by introducing a couple of properties of the interior of a set, and then we'll prove those, and then we will, like I said, wrap it up. Here's a proposition with 3 properties for the interior of a set. For a topological space, x tau, and A, which is in any subset of the underlying set X, 3 properties. 1, the interior of a set is always contained in the set. 2, A is an open set is equivalent to saying A is equal to its own interior. And part 3, the interior of an interior of a set is the same thing as the interior of a set. Now, this last one, you know, if this wasn't true, this could get really, really weird. For example, like it's nice the fact that when I take have the interior, if I take the interior of that, it's not something different, because then we could have, you know, we could talk about what's the interior of an interior of an interior of an interior, and it just gets to be ridiculous. But thankfully, that's not the case, and we just stop at one iteration. Let's go ahead and prove each one of these statements. The interior of a set is contained in the set A. Okay, let's go ahead and prove that. Well, let X be an element of the interior of a set A. Well, what does that mean? Well, if X is an element of the interior, remember the interior of the set was the union of all the open sets contained within A, well, then this must imply that there exists an open set where the open set, of course, is contained in A, and X is an element of U. In other words, if X is an element of the interior, it must be an element of one of these open sets contained in A. But since X is an since X is an element of U, and U is a subset of A, then of course X is an element of A, which implies the interior of A is contained in A. Again, the interior consists of a union of subsets of A, so therefore, clearly it's going to have to be a subset of A. 2. A is open if and only if A is equal to the interior of A. Well, let's start by proving the direction going from if A is equal to the interior, then it's open. Well, if A is equal to the interior of A, then A is equal to a union of open sets. Hence, is open. Okay? Again, just the definition of the interior, it's a union of open sets contained within A. In particular, it's a union of open sets. So if A is equal to the interior, then A is a union of open sets, which is therefore open. Now let's prove the other statement. If A is open, then A is equal to the interior. Well, if A is open, and since clearly A is a subset of A, so A is one of the possible open subsets, then the interior of A, which is equal to the union where U is an element of the open sets and U is a subset of A, so this is a union of all these open sets. Well, A is one of these, so therefore this is equal to A union, the union of U's, where U is open and U is a proper subset of A. So in other words, sort of like when we take an infinite series and I just kind of like break off the first term, what I'm doing is I'm taking a union and just sort of breaking off one of the terms. Well, all of these are a subset of A, so this is A union a subset, which of course is simply the set A. So in this case, if A was open, then the interior of A is also equal to A. Okay. Now let's prove the last statement here, where the interior of an interior is equal to the interior of A. And let me leave statement 2 up there for the moment. So proof of statement 3. Well, remember we said the interior of A is open? The interior of a set is always open. Well, now let's look at statement number 2, where I simply replace A with the interior of A. Well, the interior of A is open, so that's the left side of this biconditional. So if the interior of A is open, then this, of course, says that A, which is this set here, then the interior of A is equal to the interior of this set. And therefore, when I take two iterations of an interior, it does essentially nothing. The interior is the interior of the original set. Okay, thanks for watching, and please consider subscribing.